Okay, and I will now try to convince you that, or suggest that such a seed exists, such a pseudorandom generator exists, and it's generally believed that such a pseudorandom generator does exist, and in particular, if you believe that the SAT problem is super hard, so you not only believe that P does not equal NP, but you believe that SAT is really hard to solve, like in some sense it takes exponential time to solve, then theorems from the 80s and 90s imply that such a G exists, which is quite interesting. This is a paradigm invented in the 80s called hardness versus randomness. And I'm not going to get into very many details, but the idea of this hardness versus randomness paradigm is a way to imagine making a pseudorandom generator G that looks like this, that takes a short seed. This somehow represents a string here, maybe of length 10 log n, and tries to, this generator tries to make a long string, maybe of length n. Maybe this seed is called S. Maybe this pseudorandom string is called R. This hardness versus randomness idea, due to Nisan and Wigderson, is a way to try to imagine making such a pseudorandom generator G. And the idea is you take a bunch of subsets of the input bits, the seed bits, not necessarily contiguous, but I've just drawn them as like ellipses here. You take exactly n subsets of the seed. And let me not exactly talk about which subsets they are, but you have to be a little bit clever about this. And what you do is you take a really hard function like SAT, and you apply it. Think of SAT as a function that maps strings to bits. You apply it to all of these subsets of the seed bit. And that's how you get your n bits of output here. And somehow the idea, which is maybe kind of believable, is if this is a truly random string, and SAT is like a really complicated function that's hard for a polynomial time algorithm to understand, then maybe these bits will look totally random to a lowly polynomial time algorithm. And this construction is actually efficient because this seed is so short. All these sets have at most log n, order log n bits. So even if takes you exponential time to compute SAT, still only polynomial time to compute all of these bits. This is a vague idea, but let me just summarize what was proved about this idea over the course of like 5 or 10 years in the 90s. It culminated in a theorem due to Impagliazzo and Wigderson. This is the Impagliazzo Wigderson Theorem. And it says the following. Suppose you have what you believe is a really hard to compute Boolean function mapping strings into bits. Maybe you might think of h as like the SAT function. And it has two properties. And these are quite careful properties. One, you assume it's computable in like exponential time by Turing machines. And you want this because you want this process of generating the bits here to be polynomial time. But at the same time, you want it at the same time to say that it's actually a very challenging and hard function. And the right thing here is to say that it's not computable in much less than 2 to the order n time. And for technical reasons, you need it to not even be computable in this kind of sub-exponential time by circuits. Size by circuits. This is for all sufficiently large n. in that case, if such a hard function exists that's sort of exactly, you can compute it in exponential time, but you really need exponential time even if you're a circuit, then such a pseudo-random generator G exists, and as a consequence, BPP P equals P, which basically means every polynomial time randomized algorithm can be de-randomized to a polynomial time deterministic algorithm. So it doesn't prove that, this is true, but if you find this believable, and many people find this believable because many people believe that SAT has this property, then you're forced to conclude that de-randomization is always possible. So it's a strong assumption. It's a stronger assumption than P equals NP. It's stronger even than this assumption called the strong exponential time hypothesis, but still believable. Any questions about this? I mean, I didn't prove anything, but this is the idea. Yep.
By not computable, do you mean the worst cases that this works?
Yeah, that's a very perceptive question. The question was like, when I say not computable, does that mean worst case not computable? The answer is yes. It merely means not computable in the worst case by such circuits. And that may seem fishy in accordance with this picture, because this picture is sort of about hardness for random inputs. And SAT, for example, has the property that maybe most, random instances are maybe unsat. And therefore, if you really just use SAT here, then maybe most of these bits will be 0. And then if that's true, then for a random seed, if that's true, it's actually easy for a polynomial time algorithm to distinguish this from a truly random string, because this will be mostly filled with zeros. But this is part of the effort of Impagliazzo Wigderson. The first theorems to this effect required a stronger statement here that circuits of exponential size couldn't even be slightly correlated with the function h. But one thing they did was weaken this assumption to worst case hardness. Yep.
Why do we need this to be an NP statement like SAT? Why couldn't we use some function that's exp or something?
Yeah, it doesn't have to be SAT. This is only an example. It's just any function that has these two properties. So it should be in the complexity class called E, but it should not be computable by circuits of size 2 to the epsilon n for some constant epsilon. Yep.
So if you only use SAT, can you do something weaker?
Yes, so this thing called the Seth strong exponential time hypothesis is similar to this, but maybe it's not about hardness for circuits, just hardness for against Turing machines. The answer is yes, you can prove some weaker statements, de-randomization statements, but they're kind of complicated to state and maybe even interpret. But yeah. Okay. So in some sense, this actually kind of solves de-randomization, mostly, if you're willing to believe this strong complexity theoretic assumption. Okay. So proving something like this is even harder than proving NP does not equal P, so people don't really plan on proving this assumption anytime soon. So one thing that people have turned to do in the field of pseudo-randomness and de-randomization is they've said, okay, well, let's try to achieve de-randomization for specific polynomial time algorithms that we care about, but unconditionally. I'm not going to try to de-randomize every algorithm. I'll try to de-randomize some particular algorithm that I care about. I'm going to try to make it from randomized to deterministic. And it's maybe some ad hoc method, or by using one of these things I talked about on the earlier board, some de-randomization techniques. And we'll try to do it unconditionally. And actually, before I get into some of these specific techniques, I want to mention one unconditional result, which is pretty general in complexity theory, albeit it does not have kind of the best possible conclusion, but it's a good result, and you can sometimes use it if you care about de-randomizing your algorithms. So I've pre-written it here. This is a result by Noam Nisan from like 92 maybe. And it's a pseudo-random generator, which is pretty good at fooling not polynomial time algorithms, but space-bounded algorithms. So if you're interested in fooling all, developing a good pseudo-random generator, which is good against all algorithms that use S of n space, rather than some time bound, Nisan gives you a pseudorandom generator where the seed length, L, is S times log n. And this is less important, but the epsilon parameter is really great. It's exponentially small in S. So even for like maybe the least allowed S, log n space, it's already polynomially small. That's wonderful. And the seed length is OK. The dream in seed length is to always make this order log n, because then you can enumerate over all possible seeds in polynomial time, and it's real great. OK, so as an example, use of this theorem, if S of n is order log n, OK, then epsilon is really great. It's 1 over poly n, which means that substituting the pseudorandom bits for the truly random bits hardly makes a difference to your algorithm. It'll change the output probabilities by only 1 over poly n. The seed length is order log squared n. In particular, that means you can de-randomize in time exponential in this, which is like n to the order log n. Okay, this is often called quasi-polynomial time. It's not polynomial time, but it's a lot better than the naive algorithm of trying all possible random strings, which would take 2 to the n time. So this is a very interesting generic algorithm that is completely unconditional. There's no assumption, and it sort of quasi-polynomial time de-randomizes algorithms that use very little space. And sometimes you can use the ideas of this generator to actually get polynomial time de-randomizations for certain low space algorithms. And I won't prove this either, but there's actually 2 known proofs of this theorem, at least 2 known proofs. One of them uses a tool called pairwise independence, which is exactly what I'll talk about next. And the other proof, due to Impagliazzo, Nisan, and Wigderson, uses a tool called expander graphs, which I'll talk about, 4 lectures from now.